Okay, so to get things started, one of the questions I think I heard, there was some discussion on is, how do we scale? Are we broken? And I think this really comes from the end user perspective. And I think Ram raised a really interesting question of how do we have this composability and this flexibility that he's looking for? And, we heard from Chris's perspective in terms of, I guess, doubling down on improving the efficiency of the existing lane speeds. But I guess the question I'd like to ask the panel is, can we get there? Can we get there with, with starting with that thesis that we can start with 100 gig per lambda, for example, and go from there and maybe reusing pluggable architectures? Or do we really need to go to tighter levels of integration to get to the efficiencies we need to scale? So maybe that question, maybe Ram, if you don't mind, I'd like to start with you, and then we'll go from there.
I tend to maybe bucketize the thought process into the application area, perhaps a bit too much. To me, switches are a different beast altogether from server platforms, and every XPU appears to be a bit different. But in general, I think we're asking the questions of how big does this co-packaged optics or these transceivers need to be, right? Or how small do they need to be to be broadly applicable, to be hyper efficient, ready for integration and things like that. So that's that's one consideration. I think we need to sort of be consistent, perhaps, or have a model around how small these things need to be. And there is indeed that contention that I mentioned. The other thing is, what part of the problem are they solving? Are there other pieces of the overall system level puzzle? Like, what are we aiming at? And sometimes it feels like from a switch platform perspective, with its narrow scope, you're getting a pretty complete solution with something like CPU, right? Fairly comprehensively addressing the design complexity, the energy efficiency, the airflow problems, the front panel problems, all of those things. So that's exciting, but it doesn't seem like it's an all-in-one solution for XPUs. They need more. It's not just that piece. You really seem to need more. Then how do you really do composing? What does that switch look like? And I do think that in some of these webinars, we probably need someone to level set us on where the latest optical switching technology is. Really like to see progress, steady progress, and breakthroughs in that direction, even if these are like prototypes or advanced prototypes, right? So where exactly are they? Because they are really applicable, right? I think if you turn up the contrast and you look at these composable systems, we're not really comfortable in introducing PCIe switches, high radix switches, electrical components like that, or retimers, because of the power consumption and latency and the cost of these things. So we need to keep an eye on switching. Absolutely.
Okay. Great. So thanks, Ram. So Chris, your perspective came from kind of the networking side of things, and I think Ram's maybe coming at this maybe the compute side. Do you think your thesis still holds true when you map that onto compute infrastructure? And given what Ram was saying about maybe needing to add optical switching into the picture, does it still hold, or do you think there's new innovations required?
Well, let me not comment on that. I don't have data on that. So, Ram's the expert and Intel, but I don't have solid data on that. So I can't comment. The data I presented and what I've been working in is Ethernet. And by the way, I'm not against CPO. I mean, if John and Clint don't do what they're doing now, we're not going to have CPO in the next decade when we're going to need it. So don't misunderstand me. And it's good news for them, because if they had to deliver 2 or 3 years from now into, ship 1 million of these things, that'd be too much pressure. We shouldn't get distracted, because, then my friends at Intel and Broadcom, they feel the need to put up these diagrams and say, oh, we're going to ship this next year or the year after that. And that's really not helpful for what we need to do for the next decade. I mean, we need fundamental breakthroughs like the ones John talked about and Clint talked about, to make it realistic, and just scaling the current paradigm and being clever about packaging, it's just not going to get us there, because I mean, you go through the numbers and you don't have the breakthroughs you need in the optics and the reliability and the attach. So that's really the perspective I'm bringing to this.
Yeah. So I think what you're saying is the solutions which were kind of highlighted in the talks by some of our commercial colleagues here, and maybe you don't think are reaching far enough, and we're going to have to lean further forward, and we should, we should skip.
I don't think it's a surprise, because I'm pretty vocal. I'm fairly skeptical they're going to commercialize that in anything like the near time frame or this decade, and I'm happy to make personal bets with any of them on that. But no, I mean, if we don't, this stuff is really hard, but it does, look at, when did Larry Cauldron and Fred Kish start working on VCSELs, right? I mean, it was decade before we got him into, the mass use. So this stuff takes 10, 15 years. So, that we absolutely need to have that fundamental research done. But I think the mistake is to take existing technology and just view it as a packaging exercise, because it ain't. It's these fundamental, you look at John's diagram, I mean, that's the kind of breakthrough we need, or Clint's diagrams. That's what we're going to need to make that feasible.
Well, maybe I could ask Thomas or Manish to respond to that, right? I mean, you've got a commercial pipeline and an incremental, product roadmap that you're using. I mean, what do you say to, how do we bridge where we are right now to some of the far-reaching technologies that maybe Clint and John are showing? Is it a necessary step?
Thomas?
Yeah, no, I think it is a necessary step. I think there's so much infrastructure. There's so much riding on smooth transitions from one generation to the next. There's so much riding on hardening and maturing technology that unless you and Ram are ready to break with the past and make a discontinuity, we have to make these incremental steps, and I don't think there's any way around it, because you don't go from, I mean, it's not sort of in the past with sort of forgiving ramps and into service provider networks that you had time to fix your problems and you learn as you go along. Once you turn on for these data center deployments, it's fast, right? So it's got to work, and we got to tap into what exists. And I think that's what I was trying to convey, is that there's a lot of value we're leaving on the table in sort of a first generation, because we are constrained by the past in a sense, right? And by the ecosystem that we're trying to leverage. And that's why we can show 15 picojoule for 12 picojoule for CPO, and 3 picojoule for the compute platform, because we are unconstraining some of these things, because we're greenfield in the optical sense, if you will. So I think we have to do it, and there can be argued what exactly does that mean, this incremental approach, but it's not going to happen. We can't do it as from one big step to the finite point.
Yeah.
I mean, I think we're all agreed that CPO is not existential to networking, but the packaging and integration challenges and developments are not trivial that are going to be needed for compute. And if those are not first productized with mature device technologies such as Mach senders that have been shipping for some time, say in modules, and that's not a risk vector, then we're really going to be challenged to scale and deploy in volume when you do have to deploy for those compute applications where you are going to need 1 terabyte, 2 terabyte of die edge bandwidth on, and the only way to get that is through the fully integrated semiconductor-based devices. So,
yeah, I hear you, Manish. So, Ravi, maybe you could comment on the ability. I mean, you showed some of the pictures of the infrastructure that we use at Meta. I mean, how in your view, how do we consume integrated photonics, and how does that have to coexist with some of the pluggable transceivers that Chris showed? I mean, do we have to operate them both simultaneously? Do we have to have compatibility between these two worlds? I mean, you talked a little bit about that in your ecosystem and standardization.
So I think the way I see is going from 50T to 100T, I think we can extend pluggable optics probably few generations, but after, as we keep going in this journey, I think we will be short of extending the pluggable optics. Otherwise, it will be too much power consumption. So I think they may exist depending on your data center fabric structure. They may coexist, but eventually, I think we are migrating towards some of these either advanced packaging solution. And I think as John and even Clint show, so to me, co-package optics is a stopgap going for us to before we get to the 3D. 3D is the ultimate way where you can bring the optics closer to the electronics IC, but that technology is not mature even in the semiconductor space. So there is only one commercial product which has been announced for a 3D SOIC technology today. And yes, HBM, which is essentially a 3D technology, which is a DRAM stack. One can argue that we can use the same technology for optics and electronic switches integration. But if you want to do copper to copper or hybrid bonding type of structure, I think that's some years away. So in between, we need to rely on some packaging optimization, which is co-package optics is one way to say it's a packaging optimization.
Yeah, it sounds like you're advocating for an incremental approach there, and it's not quite ready yet to go to the full, die-to-die integration yet.
Yep.
The key point I try to make, and actually Broadcom presentation showed that beautifully, is, let's not get distracted where the savings are. I think they showed applying advanced integration to a conventional DR4, I think it was, and there was a 30% energy savings with that. Well, that's huge, right? And so a lot of this work that's being done on advanced optics, the right first place to apply it is inside the pluggable module. And if through 3 nanometers plus, the integration techniques like Broadcom described, you cut the power in half, right? And you go from 20 picojoules per bit to 10 picojoules per bit. That's huge. Multiply that by 5 million ports, and that's an awful lot of megawatts. So, to me, that's the great first place for to try out these optics technologies. And the nice thing about it is they're now isolated. You don't have to make 100 of them work. You just make one of them work. And what a wonderful payoff you get. So I thought that slide that Broadcom had, I'm sorry, who was from Broadcom?
Manish.
Yeah, that was a very nice slide, right? I mean, 30% is a big deal. And so, I really encourage us to not forget that kind of bread and butter work, because, that's in this decade, that's what's going to make the real difference.
Yep. Okay, so I'd like to switch gears here and tackle a new topic, which kind of leads on from what we were just discussing, which is, I think, Clint, in your presentation, you had a really nice chart with the three usual axes, right, of modulation, format, number of lambdas, and number of cores. And I'd like to hear what the panelists have to say about, specifically for thinking about interconnects for compute. We heard, I think it was from Thomas, that your roadmap showed, NRZ forever, going on into the distance, faster and faster. But what do people think? What's the optimal point here when we're trying to optimize for efficiency? I mean, is it, at some point, do we need to take advantage of higher order modulation? And what's the trade-off between optimizing on the optics side and taking the burden off the electronics, or placing the burden off the electronics and maybe letting the optics, have a little less bandwidth, for example? Maybe Clint, you could start responding to that.
Wow, I don't know where to start. I will say that I was super happy to see NRZ on Thomas's slide, because it feels like NRZ got sort of thrown on the trash heap way too soon when we started doing 25 gig PAM4, gigabaud PAM4. That seems like just a mistake in hindsight. We should have stuck with NRZ, so I'm glad to see that back on the roadmap. I think NRZ, you can't beat it. It's dead simple. I think if you're really concerned about efficiency, that has huge advantages to it. The problem becomes when you need a total bandwidth. And so that's when you're forced to kind of go to those other axes, all of which come with pain. So I mean, I don't have a good answer for you. Again, I think I can give you the lame answer. It depends on the application, right?
I think that's a fair answer.
If I'm doing a really short reach link, I can go parallel. If I don't have to worry about dealing with the data center's fiber infrastructure, and I sort of have a green field and a contained system, it's a much different design, framework that you would be in, and you'd make a lot of different decisions. So it's hard to have a one-size-fits-all answer. And just one final thought is, when we talk about co-packaged optics, in the back of my mind, it always feels like we should really consider that there's going to be maybe more than one flavor of co-packaged optics.
Right.
It might not all be one uniform thing that's surrounding that switch chip. We may need different types of optical interfaces that are application specific in the rack, medium reach out of the rack, longer reach, and I'm just raising that as a point too. Is that a viewpoint, or is it you got to kind of standardize everything and crank it out, everything being the same, or you'll never be able to make it or yield it?
Yep, I think that's a very, very reasonable point. So maybe John, so the technology that you showed us with the quantum dot laser obviously lends itself to going more parallel in terms of number of lambdas. Do you think leveraging that technology, you'd stick on NRZ for longer, or would you maybe try to use PAM4 in tandem with that, or do you think it's, as Clint was just saying, it's all application specific?
It's probably application specific. I think, certainly with both Kerr and mode lock lasers, you can put the wavelengths quite close together, and they're quite stable and evenly spaced. So that may push towards keeping the baud rates lower and not going to more complex formats, but just having more wavelengths. You still have obviously the temperature dependence of silicon and the rings moving. So obviously Intel had the heaters to stabilize it, and we have that in spades, right? So we've done work more recently on using silicon nitride for like AWGs and wavelength combiners, and they're very nicely, temperature independent. They have about 1/9 the temperature sensitivity of silicon, but the problem is you can't thermoptically tune them because they're 1/9 as efficient. So that's the trade-off. So as long as you can live with that, but I think the advantage of either quantum dots or Kerrs is just very large, hundreds of wavelengths. So we could generate easily 100 wavelengths today, all exactly spaced by some number. And the other nice thing, which I didn't get into, is we can yield very high numbers that are exactly on the spacing. So when you design the rings, you have to pick a space. We pick 60 gigahertz. So you've now got 20 times 60 gigahertz. The end ones have to be exactly online, and we can make lasers. The tunability of the repetition rate of the mode lock laser is enough that we can hit 60 gigahertz exactly, 60.000, which is really key. And particularly as the cavities go on chip, so when you use rings or gratings on chip rather than cleaved, then you can actually hit those spacings of the lines very precisely and with high yield. So, but I agree with Clint. I like on-off keying. That's what we evolved to get down to about the half picojoule.
I think it's important to understand why we're at PAM4. I mean, that's one of the few battles I've fought and lost in the IEEE. But that decision wasn't made because it was better for optics. The IEEE adopted PAM4 for the copper interface first in 2012, and then the optics followed with PAM4, and the reason was to use the same SerDes. So it's the reason you gave, Rob, a little bit earlier, why we don't have optimized VSR interfaces, because we don't want to put 10 different flavors of SerDes on the ASIC. And so it was an ecosystem argument, and I could scream Shannon all I want, but at the end of the day, Broadcom and Cisco and others didn't want to do two different SerDes. So that's why we have PAM4. The other thing about high order modulation, it's exactly as Clint showed, don't go beyond PAM4 because, I mean, it's diminishing returns at that point. So I certainly hope we stop. I know we're discussing PAM6 and IEEE, but please let's not do that because, Clint exactly showed that it just gets ridiculous after PAM4, it's diminishing returns. But that's the reason it was. And I think Thomas is right. For CPO, I don't think we're going to avoid NRZ, which means, again, a huge paradigm shift. And the reason for that is you got all these SerDes and, crosstalk is going to be the issue you got to fight. And so, I don't even know if it's a solvable problem. I don't know if Broadcom wants to fess up about their crosstalk issues with the co-packaging they're doing. But my suspicion is if you got 512 SerDes in an ASIC, the crosstalk's just going to be monstrous. And so you got to do everything you possibly can. And NRZ is like this huge low-hanging fruit. So
yeah, I mean,
I tend to agree with Thomas on that.
Yeah, I mean, I think you raise a good point, which is the role of standardization in this, right? And maybe if we had a blank sheet of paper or we went back and look at the application space of compute interconnects, we might choose NRZ. Manish, do you agree with that view? Do you say if you were building, or maybe a Thomas as well, if you were building an XPU interconnect, would you go back and look at NRZ, or do you think there's enough benefit in terms of maybe beachfront efficiency or number of wires you have to run to stick with PAM4 for longer? Maybe Manish, you could answer this first.
Yeah, well, I believe Thomas showed, if I understand that architecture well, I think that when you start looking at these compute interfaces, if you're doing co-packaging, you're going to have that conversion of whatever the incoming signal is right next to your PIC. Then I think that your widened parallel input at whatever low speed signal you have coming in, which will be some type of NRZ, your conversion can be to anything. Suddenly your optical out can be matched to whatever your application is. Whether you're going a few meters for a disaggregated memory or something even longer reach coherent, depending on what you input. So if that's where we're migrating to anyway, with kind of chiplet technologies, as you progress to some of the higher bandwidths off of most of these ASICs, then I think it becomes a lot more, that could be a direction we're taking anyway. I think in the short term, we'll see when we're co-packaging 512 lanes, Chris. We'll definitely let you know where we are on the crosstalk there. But so far,
please publish. By the way, if you just look at 200G today, with it, not when we first started because we couldn't do 50 gigabaud, but today the technology's matured. If you just switch from 50G PAM4 to 50G NRZ. And obviously you can't do it because of interoperability. That's at least half a watt right there. Just that would get you, at about half a watt. Obviously, we're not going to do it because now we'd have two flavors, but it's significant.
Well, and let me interject one thing is when we went to PAM4, I think I hated it more than maybe I should because I was at IBM at the time and we were talking all HPC interconnects. And so when we went to PAM4, we went to FEC, which was just a non-starter for sort of conventional supercomputer interconnects. Do we care about that PAM4 latency anymore for these more computation intensive things that are going on in the data center, the AI ML, or is it's okay that we always have to have that FEC now? We're used to it.
Well, if you leave the Ethernet, I mean, no one says it has to be 100 nanosecond kpFEC. There's sort of intermediate solutions, but like I said in my talk, we are looking at greenfield from an optical point of view. So why not make the right decision and not even introduce it in the first place?
Well, the reason we have NRZ at 100G is because of IBM, right? We had this big fight between Broadcom and IBM for 25 gig lanes. And, we compromised. We had both 25G PAM4 and 25G NRZ because, two titans fighting it out. And then NRZ just prevailed because it's better. Now at 50G, IBM was getting trashed at that point. So there was no heavyweight to counter the PAM4 steamroller. And that's why in 2012, we adopted PAM4. I mean, these things are not linear, person, business, unrelated things. We don't sit there and make the best possible decisions. But, if IBM had been there in 2012, we might have NRZ.
Well, and I guess though I heard Ethernet with Thomas, and that's also my main maybe point of confusion, or I've just got an outdated historical reference point, but none of those supercomputer networks use Ethernet. Right. It's too much latency. So again, what does the network look like? What's the protocol, and how much latency can you tolerate?
Well, maybe we could take. Sorry, Rob, you were about to say something.
Yeah, well, I've been just listening in the background for a long time, and so this is something I care about. For the NVIDIA clusters, where we really do care about latency, and specifically on NVLink, we stuck with NRZ until the next generation, where we're begrudgingly adopting PAM4, and we've designed NFEC, but we always turn it off whenever we can, because it actually matters. It's actually measurable how much of a throughput impact you have. Having said all of that, we've been architecturally accommodating longer latencies in the transactions. It's really, really hard. You may not think it's hard. It's very hard. And it's impactful, and it does compromise our throughput. So I would love if we didn't have to do that. I have a hard time believing we won't be stuck doing it, but I completely agree with you, Clint, that it's important.
Rob, could you elaborate on what type of applications? Is this an AI ML sensitivity or HPC sensitivity?
AI. That is that's the thing I pay attention to. It's a huge driver of our business.
Sure.
But and the bandwidth there is expanding dramatically. That's what I was asking for, 100x throughput improvement. We could use it today.
I have a quick question. How much have the current pruning methodologies penetrated into the production, or is it, or the AI methodology is still largely, let's call them roughly brute force? I mean, so if you'd like me to sort of describe a little bit better, but so I'm asking about the production out there. Is there any of the modern meta learning, pruning, any of that being deployed at large scale?
By you mean the neural network pruning?
Yes.
It is. It's being used, but typically not in the training. You usually don't know a priori what you want to prune until you have trained enough to see what connections aren't being used very much. So now, if you have something that's pre-trained and you're just doing incremental training, then yes, you can have that pruned. So there is some use in it. I personally don't see that much, because I'm usually dealing with the people who are trying new things and trying to push the envelope. It's certainly used in low-end inference, places where you desperately want to save power. So in a mobile device or something like that, it's definitely used.
That's a very good point, that most of the work that is being done out there is really post initial learning. There are actually methodologies in the academic sphere that are now succeeding in pruning at very early stages. But I understand the answer, that those are not being used at scale yet. Thanks.
Yeah.
So if we can maybe just come back to the final kind of piece of the panel discussion here, I was hoping that we could maybe ask the panelists if we could reach consensus. It's a very lofty goal, I recognize. I was wondering if we could reach consensus on this table. So maybe filling out this lower section right here. Do we think we have enough consensus amongst the panelists here to put some numbers in here, or at least maybe talk about the considerations? Are these the right, maybe I'll ask the open question first. Are these the right interface classes that we should be thinking about? Shelf, rack, and row, and these the kind of distances? Maybe that's the maybe an easy question that we might be able to get off the table first.
You could add one more row, which is the longer distances, right? Either intra or inter data center, but maybe those are covered by the blue.
Yeah, I was kind of thinking that those were already addressed here, and those are likely to be, as we go to higher bandwidths, those are likely to be coherent technologies, and so maybe less compute-centric and more network-centric. At least that's kind of what I was thinking, but I'm certainly open to, I mean, if we can get, low latency, low power coherent to go, several kilometers, then maybe I need to rethink that thought.
And what time frame are you thinking of for this? Because that would affect the answer here a bit.
Yeah, I mean, I recognize this is a moving target, right? So it's a hard question to answer. But I was at least, thinking of maybe just say, I don't know, 5 to 10 year time frame. It's probably the right scope to think about this. I mean, what I was hearing was, I was hearing some people say that NRZ, use NRZ as long as we can. Is that a fair statement? And through at least through 100 gig per lane, is that, or not?
I agree with that, Rob. I think especially for that first row, we'd like to use NRZ as far as we can.
Okay.
Well, there's no reason in optics not to use NRZ forever, because the single mode channel is, it's tens of terahertz of bandwidth. So it'll be a long time before you start getting into channel limitations like you do in copper. And then assuming that you keep advancing your packaging and your electronics so they don't limit you, you can just always crank the baud rate up. But then you get into the issues of ecosystem. If you're trying to have common SerDes with the copper channel, which is band limited, then you can't do that for the copper channel. So now you start, having the copper modulation be different than the optical. That's a fairly profound implication, as you pointed out, just in VSR versus LR on an ASIC, right? Never mind different modulation. So these are now business and other issues that come in. But just from a performance standpoint, for optics, NRZ or as Clint pointed out, if you're going to go coherent, it's QPSK. That you just, it's just overwhelmingly the best thing to do. You go to PAM4 and literally you're talking about a 3 dB hit.
And do we think, John, you were talking about the capacitance and needing to, basically put the electronics and the optics in, as close proximity as possible. Do you think, is 100 gig NRZ feasible? And maybe the same question to Thomas, because you had something like that in your roadmap too.
I think so, yes.
Okay. Thomas, you agree with that?
Yeah, absolutely. Absolutely.
Once we are at the row level, I think the sensitivity to NRZ goes down, right? It's in the sense it's not that critical. We don't have to wait for 100 gig NRZ to really happen and really work. You can work with 100 gig PAM4.
But isn't your row application here sort of pooling? So you've got racks of memory, racks of processors, and in that case, doesn't that NRZ versus PAM4 latency become relevant?
It does. It's just that scaling memory disaggregation at the row level. It's sort of a still thought of blue sky thing.
Okay.
If you have hundreds of nanoseconds of latency, then the PAM4 latency is probably incrementally not as important. I wonder more about, when I look at the row, do you need the same kind of bandwidth and bandwidth density as you would have within a rack or within a shelf? And it seems like this would have opportunity for a different optimization point, at least.
Got it. So I think that's an important point. Like when you get to this, the time of flight latency certainly dominates. And then what about?
I had a question. So on the optical interconnect shelf, that kind of means like chassis, right?
Yes.
I mean, I'm not advocating anything here, but I'm just questioning. I mean, correct me if I'm wrong. You're talking about less than 8 inches.
Mm-hmm. That's right.
I mean, like any of the OAM systems today, those 8 OAMs, there's definitely more than 8 inches between, the connectors on, two ends. You got 2 rows of OAM in a system today, and there's definitely more than 8 inches between, connector here and connector here at those. And I mean, if you just extend it to like anything else, let's just say you even had like a CPU server, for example, and you got dual socket CPU there, and you've got, at the other end of the chassis, you've got SSDs or, I don't know, anything else. It just seems like less than 8 inches. Now, again, I'm not advocating it. I'm just questioning. That seems like really short.
Yeah. Well, so maybe that's an interesting question. So maybe then, I mean, what I'm really hearing is, and maybe this is a question to the optics experts on the call, can we converge? I mean, do these two spaces have enough in common that, once I get into fiber, I don't care whether it's, 20 centimeters, 5 meters, it's all a question anyway. I'm not worried about any kind of dispersion in that regime, so it doesn't really matter, right? So maybe these 3 interface classes are based on, physical packaging delineations, which kind of we've inherited. But once you get into optics, it doesn't matter. Is that a fair statement? Do people think?
Well, it's a fair statement if you talk about single mode, right? Because for single mode, for these reaches, it's the connector loss, not the fiber loss that matters. But if you have a different technology, let's say multi-mode, those may be limited to a few meters if you don't have a coherent source. So, but for single mode, certainly this is, you wouldn't differentiate between those.
But is this all single mode? Because I look at 0.2 or 5 meters and I think, why isn't anyone talking about VCSELs and multi-mode fiber?
Boy,
that's a good question.
Because we're not dinosaurs like you, Clint.
I know.
We're looking forward.
There's the Chris I wanted to see.
Hey, a lot of us have dark VCSEL pasts, though. Even John, he just laughed, but he does. Some VCSEL skeletons in his closet.
Well, today, what's shipping VCSELs are the most energy efficient right now. Everybody talks a good game, but right now in volume, the VCSEL is the most energy efficient.
So Rob, with these, right, I think we, in order to do justice to the numbers and the rows here, we've got to imagine what is it that we're actually trying to do within that shelf or rack or row, right? And in a certain time frame too, right? And how we think about it is that shelf plus minus is a really interesting domain, because you don't have these heavy, high radix optical switching like technologies that allow you to effectively pool things at a rack level or at a row level yet, right? Until we have that kind of cool technology, it's very difficult for us to imagine disaggregation going into racks and rows. So that domain in which you can effectively pool, we need to understand what that is. And that feels like more at a shelf-like granularity and barely at a rack-like granularity, but certainly not row granularity.
Yeah, I hear what you're saying, Ron. But let's assume, just hypothetically, we were to give you an interconnect solution that would enable you to disaggregate at the rack level with, 1e minus 15 error rate, and then you'd have to eat the time of flight latency with, a short FEC overhead or a CRC or something on top of that. Could you even accommodate the time of flight latency, right? I mean, is on the order of tens of nanoseconds or 25 nanoseconds or 50 nanoseconds, is that at that point, has physics broken what you need to do with your memory hierarchy? Or is that okay?
I think those numbers look fine, but the connectivity is not clear yet, right? What I'm trying to say is that you have enough connectivity from physical endpoints that you will actually have to introduce a good low latency, low power switching technology, which you don't have.
I see. So that's why you were advocating for an optical switch to enable that path as a potential technology.
If you're within a smaller realm like a shelf, then you can do the connectivity without that switch.
Okay, got it.
So Rob, I wonder if rather than reach, what matters there might be margin. One solution being a lower margin than the other, at least if it is single mode fiber.
So I mean, link margin, link loss tolerance. You mean?
Right.
Is that, yeah. Okay. Yeah, that's a good way of thinking about it. So it sounds though if what Ram's asking for is true, when he needs an optical switch, we might need more than 4 dB or 3 dB.
Yeah.
Because the optical switch losses, are in the order of, I mean, the best ones are in the order of that range already before you've added any other connector loss.
Yep.
Unless we can go we can maybe, I don't know, maybe John, maybe we could add I think Thomas, you had on your slide, you had some optical amplifiers, I think on one of your picks. Maybe we could have an optical crossbar with some amplification built in to effectively make it lossless.
Yeah.
I know SOAs have their own challenges.
I can send you some drawings. I think John can too, from the good old days. Switches with SOAs. It's certainly, I mean, it doesn't solve everything though. I mean, I think that's the reality of photonic switching, and I showed a photonic switch, but it's far from a solved problem. I mean, the one I'll give you is polarization. That's the first one to chew on. How do you handle polarization? It's not easy. And then there's the loss. I think we're a little ways out from that being practical.
By the way, once you start talking about SOAs, again, that's where NRZ starts having additional advantages, because with PAM4, the noise onto the lower levels from something like an SOA starts dominating your BER, and now you again either have to compress the waveform or you take disproportionate SNR hits, starting to offset the amplification gain. So, once you're talking about SOA in particular technology, the simpler the modulation format, the better off you are.
QPSK does pretty well too.
Right, even better, right?
Rob, should we try and tackle the efficiency requirements?
I was just going to go there next. So yeah, this column right here. What do people think about this? I mean, if we're converging these two spaces together right here, do we think we at least? I think Thomas, you had from my notes, was it a 3 or 4 picojoule per bit number for this?
I absolutely do not think that's the end game. I think that's what the sort of first generation line of sight to. I don't think that's where we should set our goals higher or lower, maybe. But I think that's what is feasible in a reasonable
Wait,
time.
isn't like Ayer Labs claiming 5 picojoules per bit today because they have a different type of technology? I haven't independently reviewed their numbers, but they seem like credible people. That's a very impressive number.
Yeah, I don't know. I can't remember off the top of my head, but maybe John, I mean, for the approach that you're doing with pipes, I mean, what's your bottoms up target there? I can't remember whether you showed that in your slides.
I do. I mean, certainly, I think 1 picojoule per bit is achievable there.
And what's just maybe one of the things?
But is it required? I mean, to me, it's not an issue of what's possible, but rather because things get more expensive, right? As you lower that number.
Well, yeah, and I think the question is, what incumbent technologies are you trying to displace, right? So if you come in with 4 picojoules per bit down here, does it limit the application space where you're going to try absolutely hard not to use it, which is always where we've been with optics relative to copper? But but is there a tipping point where you say, if I can get to like a picojoule per bit, just as a hypothetical, then does that unlock a bunch of applications where you say, oh, it's good enough, I'm just going to do it because it's just so much more flexible. It solves so many other problems for me at the system level, like power density, power delivery, cooling, etc. That I'm just going to do it.
Rob, what's the application for that though? I might have missed that, because if I look at the upper part of the table, the only thing at that distance scale is system memory.
Well, right. So, okay. So maybe talking about this one, maybe Ravi, you could chime in here. One of the challenges that I hear about for HBMs is as the as the accelerator gets more and more power hungry, trying to cool those HBMs and keep them within their temperature range is becoming harder and harder. And so remoting them is desirable, but there's no way to do that at high bandwidth and low power.
Yeah, so I think, Rob, some of the challenges with HBM is also we are seeing the temperature gradient from top of the stack to the bottom of the stack, because now HBMs are coming into 8 and 16. So that is also creating a lot of gradient and creating an efficient cooling system around that. So the thought process is, can we do system level disaggregation where we can have a common place where we have all the memory and then our accelerator can access all that memory. So today, because of the packaging technology limitation, the HBMs are within the 5 millimeter distance to the accelerator using some kind of a CoWoS or a fan-out type of technology. Now, how can we increase that distance and still will have low latency bandwidth access?
Yeah.
And will not burn more power.
I don't know whether Rob's still on the phone, but I'd love to hear what your thoughts are about if you could remote more HBMs and locate them near your GPU devices. Would that be desirable?
So, I mean, I think practically speaking, take a look at the the package sizes that we're already pushing, and I mean, maybe I'm looking too rear view mirror, so I apologize for that. But like the going rate for OAM 2.0 is like 102 millimeters wide for the OAM, precisely so you can get 4 of them across a system and 2 rows. So we have a problem with the package size already, right? And so like one of the questions I was asking, well, what the heck are we talking about? 150 by 150 square millimeter package is not very well going to fit on something that is only 102 millimeters wide. I mean, the OAM module, which is like a physical PCB for a card. But so there's a couple thoughts. Number one, we got to think about, which problem are we trying to solve and the granularity there. The second thing is, everybody's all paranoid. This is being recorded. I should tone it down just slightly. There's this fear of double rate refresh on HBM, but it's actually only a 7% hit, I hate to say it that way, on the delivered memory bandwidth. And it opens up a whole lot more temperature range. So, there's a trade-off. I mean, I think we're gonna have to use all the knobs that are available before we ever get to using optics to disaggregate HBM. Second thing is, when you do go to disaggregating the HBM, we certainly have limits. I mean, these are obvious, but the HBM's only a certain number of millimeters wide. There's a certain amount of beachfront. The bit rate on HBM is on its own, dramatically increasing path. And so, obviously we'd have to be able to accommodate that bandwidth in, similar beachfront. And then, the size of the optical solution, certainly there has to be constraints on that as well, right? So, I mean, yeah, in theory, it'd be great to have an HBM DIMM. In practice, once you have that, where do you put the DIMM? Like, okay, we already have the system, so now you got to disaggregate it a long way away, I think. I mean, I don't know where in the system all these, like, let's say we got these optical cables to DIMMs, where do the DIMMs live? So that just creates another, kind of practical problem. So like I'm highly skeptical about the the crossover point, at which point it's going to make sense to actually disaggregate the HBM. I think that's like, of all the problems we have to solve, that's probably not at the top of the list.
Rob, I tend to think of that 0.5 picojoules per bit as a bit of a stretch goal for the shelf case because of the points that Frank mentioned. But I think the other reference points are the picojoules per bit and 6 right below, right? If we are in that range, then it's a good, we can make some interesting things happen to the shelf.
So you're saying, Ram, if you could get here to less than, I'm just going to put less than 5, that would be success in your view?
In the line above, at the shelf level.
In the line above.
Yeah.
Okay. Well, I think what we were saying was, from an optical technology perspective, we could maybe converge these two spaces together with Chris's comments about multi-mode notwithstanding. But if that's true, then one would suggest the other.
Yeah.
Right. Okay. Well, very good. What about these numbers right here for the total interface bandwidth? And I apologize to the people who are more on the computer science side of the house, because I think in gigabits per second, not gigabytes per second. So we'll have to do some multiplying by 8 there. But I mean, are these the right kind of interface, total interface bandwidth we should be thinking about? And there's multiple ways to think about that. I mean, it could be per fiber, it could be using multiple fibers, constituting one port, quote unquote. But I mean, is that are these the right numbers to be thinking about, or should we be thinking about more skinnier pipes?
I wonder if it's more productive in terms of thinking about solution to think of a linear density or shoreline density, bandwidth density, and then you can scale to your application if you have a density number that's appropriate.
Yeah,
right.
That could be the other thing that is, I mean, a consideration. Let's say a consideration. We're currently, I think I said we're exposing 128 lanes of SerDes from that OAM, right? And if those were going to change from electrical to optical, I mean, you could just imagine the bandwidth of 128 lanes of SerDes. Electrically, that's going to happen at 112 gigabits per second, right? And you can imagine needing to get beyond that. So, one of the questions kind of becomes, and this is really for the hyperscalers, but like, what is serviceable at a data center, right? I mean, the whole reason for OAM was precisely so you could have single axis insertion and you're done. And I mean, I think the thing that, folks at Meta can comment, folks at Microsoft or Google can comment, but well, actually I saw Google had a bunch of cables external, but I mean, it seems really difficult to be in a situation where you got this octopus, and it's not just one octopus, there's like currently 8 of them. Now, I don't know if that means we have to go to bigger pieces of compute and fewer of them in a system, but I mean, we're talking about having multiple terabytes per second per accelerator. I don't want to say very soon. I'll just say very soon, right? Multiple terabytes per accelerator of communication bandwidth, and that doesn't necessarily have to be, this little like point-to-point thing, right? I mean, if you just look at if you had a switch. You want to take one big fat pipe to a switch because humans can deal with, connecting one cable a lot better than they can with a gazillion cables, right?
I mean, I think Frank, you had a number of really good themes there. I think the first one is if you go back to this picture right here, and I apologize, this is very cartoony, but this could represent a bunch of AOMs on a system meshed together, right? And I think the thesis is, as we go to higher and higher lane speeds, to your point, we're already bringing out 128 SerDes pairs on these things. You go to 200 gig, I can no longer put this on a PCB because signal integrity won't let me. So I need another kind of interconnect. So I already, to your point, if maybe the right problem to solve first is, I need a low latency accelerator to accelerator interconnect in optical. And then I no longer have 8 of these things on a PCB. Maybe I have 2 of them or 4 of them. And so maybe the serviceability becomes easier, or my unit of serviceability perhaps becomes a shelf, and I have a multi-core fiber bundle which I can plug in with one connector and then take that to some kind of a switch. Does that seem to make sense?
Yeah, I mean, it could be. It could be. But then, I guess what I'm saying is, if we were going to take from each of those instead of having all this point-to-point stuff going on between accelerators, or in the Nvidia case right now, it's from each accelerator into a plane of switches. If that was to move to, like, I don't know, a rack level switch, and you were just going to put optics from each one of those compute sleds into a switch, we still, I think, need to limit the number of individual connections that humans have to. I mean, unless we're going to get robots that can do it for us. It's like everybody hates cabling. Humans can mess up cabling. Cabling causes problems. Yada yada yada. So,
what do we mean by interface in that table? Like 1,000 gigabits per second per interface. What's an interface?
This table right here, Ron?
Yeah.
What I meant was, I'm thinking like, if you're thinking in the networking world, I'll be thinking port, right? Or,
it's not per lambda. You're not talking about per lambda?
No. I'm thinking about per connection between, per bus, if that's not a very trendy word these days, but, per bus instance.
I don't know if Tom disagrees. I think for us, it'll start to look like per engine. Engine. What are you, especially, and then that will define how many engines you need per ASIC. So, and then from there you can go into number of wavelengths and mux demux and how many fibers you need, but ensuring that you get the right, ultimately the right shoreline density.
Yep.
Thomas said it correctly, is the correct.
Right. I think that's one thing I'm missing from this table from our discussion is shoreline density. And I think Thomas, I think it was Thomas said PCIe 6 was your bogey and you were trying to beat that. Is that right?
That's what we used internally, saying if we can't do better than that, what are we really doing?
Yeah, and I guess what I would say is for some of this market, the AI training market in particular, you can see that. I didn't show it, but our competition, Rob's not on here, but they were already at 50 gigabits per second with A100. Publicly they've stated in multiple forums they're doubling everything every 2 years, so they're gonna be 100 gigabit per second this year. PCIe is so outdated. Forget about it. When it comes to AI scale, AI interconnect cannot live on PCIe. 64 gigabit per second, PAM4 with PCIe Gen 6 at the end of 2025 is just like so out of date, so irrelevant to AI. That is not a bogey, right? I mean, just take the words that they said, double everything every 2 years. Jensen said it on stage. They're going to have 800 gigabit. I guess he was mentioning InfiniBand, but think the same SerDes for everything else in 2024, right? And we know 800 gigabit exists in Ethernet switches, even sooner than that. So, the target should not be set by PCIe. That is like too yesteryear.
Go ahead.
No, I think there was more of a density consideration that when we look at the 100 gig and 200 gig Ethernet SerDes IP is actually worse in density than some of the predictions for PCIe. And that's why I said PCIe from a density point of view was actually a reasonable target to set. I'm not saying that it's a reference for bandwidth or for what kind of port we should replicate. Absolutely.
Fair. And I think the other thing, it's probably been said somewhere, is you're looking at chiplets, right? So if you're going to do this, I don't know if the co-packaged optics is the right term, but if you're going to do this integration where you're die stacking your photonics IC, on the same ASIC, if you will, for lack of a better term, you're not going to end up using one of these SerDes interfaces anyway. You're going to use some tiny low fraction picojoule per bit, die-to-die interconnect type interface at massive bandwidth. So,
and are you referring more for a 3D stacking point of view in this example, or is it?
Yeah, that's what I'm saying. I mean, it's going to have to. Let's put it this way: we're going to stay electrical. I'm not making a statement for AMD, but I'm just saying the industry is going to stay electrical until it doesn't make sense to stay electrical anymore, right? And so, if we just take the Nvidia statement, everything's going to double every 2 years. We're going to run out of electrical pretty fast here.
Yeah. Would you be able to, you mentioned the 128 SerDes, so does that correspond to a die edge of what, about 20 millimeter or something?
I don't have that right offhand. You can kind of look at there was a cartoonish die photo and we've published a white paper on the MI250X thing, but that thing goes on an OAM. So each end of the OAM has 4x16 SerDes, if you want to think of it that way. So 64 SerDes. So you could kind of look at the die photo and maybe get an idea of, okay, at one end of there were two big die on there. Each one of them exposed, 2 edges covered with HBM and 2 other edges. And you can imagine the 2 other edges is where 64 lanes of SerDes live. And I don't know if there's enough detail in those die photos to, kind of exactly figure out where the SerDes are and how much of that is SerDes, but I don't have that right offhand. And yeah.
I mean, Rob, it would be a methodology to get to that shoreline density. So
yeah, and then I think HBM also has I think it has a well-known shoreline density in the industry.
Well, everyone, I want to be respectful of people's calendars because I realize we've gone a half an hour over. So thank you very much for sticking with us. And the panel discussion was great. I really enjoyed that. I thought we covered a lot of ground, and I will endeavor to tune up this table with some of the things that I learned here. So thanks again for all the speakers for this afternoon session and to our panelists. And yeah, I think over to you, John, if you want to have any closing remarks.
I just want to second your thanks to all the speakers and all the participants. I think it's been a great meeting, and certainly on behalf of IE, I really appreciate it and hope we can gather together all this information and look forward to future collaborations. Catherine, you want to say a few closing remarks?
I echo a lot of the same sentiments. It's been a wonderful forum today. I personally have enjoyed it very much. What great collaboration. And I really appreciate the discussions I heard, the level of discussions, right? It feels very collaborative, which is excellent. And thank you for your time today. I in both of the sessions, the morning session and the afternoon, I think we came out of that with some really solid takeaways. Barath's list of 8 points and Rob filling out this table, which I think is going to be very useful for guiding our thoughts and our innovation directions. So thank you. Yeah, I don't have any other comments. I think let's call this a wrap and let everyone go. I think this has been wonderful use of time today. Thank you.